The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
All right, let's go to our next speaker. Well, before I start, I'd like to thank all the audience for staying the last presentation in the first part of this session. Indeed, during the session, we have listened to very interesting presentations discussing about the behavior of high-strength concrete columns. In my presentations, I'm more focused on some design-related issues for high-strength concrete columns. But clearly, in order to use high-strength concrete columns, we have to design them using the code. And as a first stage of the designing columns, we generally calculate the code design strengths. And we typically use concrete stress block for that purpose. If you look at the current ACI 318 expressions of stress block, they are mainly based on normal strength concrete and to some extent over high strength concrete. And there are many studies available which reported that the current ACI 318 expressions may overpredict the high strength concrete columns. And as a result, there are several alternative expressions of the stress block parameters are available. But there are some questions are still remaining. First question is, if potentially the ACI 318 expressions have some issues, what is the critical conditions? And for example, which concrete strengths we have to be careful for using the current ACI 318 expression. And if we want to use the other design expressions among various design expressions, which one do we have to choose? And in addition to that, if there is some code-related strength calculation issues for columns, is there any other similar concrete members which has similar problems? So I hope that during my presentation I can answer some of the questions. This study was co-worked by Professor Frederick at the University of Texas at Austin. So if you look at the concrete stress block, basically it has two components. They are alpha 1 and beta 1 parameters. And in the ACI 318 code, alpha 1 has a constant value of 0.85, and the beta 1 parameter varies from 0.85 to 0.65, depending on the concrete strength. Since the adoption in Chapter 10 about the concept of a concrete stress block, this concept has widely spread, influenced to the other design provisions. For example, later Chapter 10, for calculating concrete bearing strengths, the alpha 1 parameter, which is 0.85, is used in their equation. Chapter 18, pre-stressed concrete, use beta 1 expression. Chapter 22 and Appendix 8, plain concrete and Strut and high model use the alpha 1 expression in their design equations. And as I mentioned previously, many test results indicate that the current ACI expression has tendency of over-predicting the high-strength concrete columns. Some examples are shown in the plot. The data points represent the experimentally obtained column strengths, and dotted line, not solid line, dotted line presents the code predicted strengths. And you can see that the code predicted strength is greater than the actual concrete column strengths. And as I also mentioned, that little guideline has been provided, for example, for the concrete strengths, which the current ACI 318 expression should be avoided or should be used with caution. And even though many other design expressions of stress block are available, there is no comparative comparison evaluating their performance. And also, the impact of any change of stress block on other design provisions never been examined. So in the table, I'm showing some the code expressions of different stress block. The New Zealand code and the Canadian code have different expressions to address some of these design issues related to high-strength concrete. Also, there are many other proposed expressions done by various researchers. So let's look at how different they are. If you look at the plot A, which is the alpha 1 parameter, the ACI code has the only expression which the alpha 1 has a constant value of 0.85. All other code and the proposed expressions have the same tendency that alpha 1 parameter is decreases with the increase of the concrete strength. And in case of beta 1 parameter, ACI code expression provides the lowest value among all other the expressions. One observation we can make is, even though they are different, in general, the range of the alpha 1 and the beta 1 parameter varies from 0.85 to 0.65, except a few cases. So in general, we can say that the upper bound and lower bound are close to 0.85 and 0.65. So I look at the influence of the difference of the alpha 1 and beta 1 parameters on interaction curve. The top two curve presents for the cases where the same alpha 1 parameter of 0.85 is used, but different beta 1 parameters. So basically, the reduction of beta 1 parameter only influence the interaction curve around balanced load regions. When the actual load is small, or when the actual load is very large, there is no influence on the PM interaction curve due to the change of beta 1 parameter. On the other hand, the alpha 1 parameter has a more global influence on the interaction curve. But still, when the actual load is small, there is no change. So we can summarize that the change of beta 1 parameter has a small influence on the PM interaction curve compared to alpha 1 parameter. And the interaction curves are insensitive to the difference of the expressions when the actual load is small. For example, when the actual load is less than 0.1 times the nominal actual strength. So if the design focus is beam design, the flexural strength of the high strength concrete beams can be calculated using the ACI 318 expressions, introduce any other expressions, and they will provide similar results. Then why the members with a small actual load does not affect by the change of the concrete stress block difference? That's because these members are tension controlled. The strength of tension controlled members are predominantly governed by the yielding of rebar, not by the concrete strength. So the difference in the concrete strength parameter becomes insensitive. In truth, for this, the tension controlled member, there is a little benefit of using high-strength concrete. So we can make a quick conclusion that when the actual load is small, ACI 318 current expression does not have any issues for the design-wise. So we first look at the influence of different stress block parameter in the context of Chapter 10 in ACI 318. For this purpose, we use 224 database. They are all rectangular concrete columns, and if you look at the ranges of the parameter, such as concrete strength, rebar strength, and applied in the actual loads, we can see that this database is a sort of a comprehensive database for evaluating the behavior of the columns. One of the challenges using large database and then comparing the performance of the different stress block using the interaction curve is the interaction curve itself is dependent on concrete strength, rebar strength, the layout of rebar, size of columns, and the amount of rebar. So if we use 224 database, we may end up more than 100 different interaction curves, resulting in the comparison, makes the comparison almost impossible. So what we have done is we basically look at the interaction curve and then found that the most important piece of information from the purpose of the comparison of performance is we are actually looking at where the location of the data point with respect to the interaction curve. In other words, we do not really concern what is the actual data point value is, or what is the actual strengths, the interaction curves are. So we basically introduced a normalized PM interaction curve. What it is, we came up with a fictitious column detail, which is shown here. And using these fictitious column details, we can calculate corresponding fictitious PM interaction curve, which we call the normalized interaction curve. And we do have a original data. In this slide, I'm showing the three different data points with the three different interaction curves. And basically, we are converting the data point to normalize the curve by maintaining their locations with respect to code calculated actual strengths and code calculated flexural strengths. So this is the results. So this is the comparison when we use the current ACI 318. So the plot A presents the columns with the concrete strength less than 8 KSI. Plot B shows the concrete strength greater than 8 KSI. We just consider that less than 8 KSI, they are sort of normal, close to normal strength concrete. Over 8 KSI, that's more close to nowadays high strength concrete. And if you look at the plot A, you can find that even for normal strength concrete, if you look at some data points, the code still overpredict their strength. So this overprediction is actually not only applies for high strength concrete, but for normal strength concrete. But knowing that code also has a reduction factor, we can see that the large safety margins are maintained throughout all the data points, regardless they are overpredicted or not. And the amount of prediction is very small. And also note that the code has the limitations on the applied in the actual load, which is 0.8 times feet times P0 for rectilinear confining reinforcement. So if you calculate the number, and 0.8 times phi, which is 0.65, the resulting number is 0.52. So any data points which are located above these limitations make sense for the research purpose, but for the practical current design-wise, only the data points located below this limitation is going to be meaningful. If we move to plot B for high-strength concrete, yes, we can see that some trend that the more data shows the code of predicted their strengths, also the amount of the prediction becomes much more severe. So I look at a little bit more detail. Now, figure A shows the concrete strengths between 8 KSI to 12 KSI. Yes, we can see some data points show some predicted code strengths. But if we limit the data point which satisfy the code, the actual load limitations, suddenly all the data points looks great. They looks all acceptable. So we can conclude that maybe or probably the current ACI 318 code can be used for the practical column design up to the concrete strength of 12 KSI. When the concrete strength is greater than 12 KSI, yes, the ACI code has some tendency of predictions. And especially if you look at the data points, which is triangular, that is greater than 16 KSI, most data points are located on the unconservative side. So in this case, when the concrete strength is greater than 12 KSI, when the actual load is small, then ACI code expression may be still used. But if you are dealing with the columns with a high actual load, then the use of the ACI code is not going to be recommended. Let's move to the other expression, Canadian code. If you look at the normal strength concrete, their performance is similar to what we saw in the ACI code. However, if you look at the high strength concrete, suddenly they become more conservative than the normal strength concrete. So we can say that Canadian code is a little bit conservative side. New Zealand code, similar conservatisms are maintained for both normal strength and high strength concrete, which is good. The expressions proposed by Ibrahim and MacGregor, the performance of a high strength concrete shows in between the Canadian and New Zealand code. They are acceptable. Proposals made by Bechtel, well, one of the authors is actually me. It's hard to tell, but in my opinion, that looks okay. The proposals made by Obakaloglu and Sajoglu, they also looks great. In case of the expressions given by Azizinamini, also shows some conservative tendency for high-strength concrete. Actually, all the data points with the concrete strength greater than 12 KSI are on the conservative side. And some data points are actually located outside regions of this figure. So they are actually excessively conservative side. So in summary, the current expression of the ACI has some tendency of prediction when the concrete strength becomes higher. And this tendency becomes evident when the concrete strength is greater than 8 KSI and the actual load is high. However, for practical column design purpose, it can be used up to the concrete strength of 8 KSI safely, and when the concrete strength is greater than 8 KSI, they may be used when the actual load is small, but caution will be required when the actual load is large. Regardless of the difference of each expressions, those of New Zealand code, Ibrahim and MacGregor, Vera and Ovakaloglu and Sajioglu showed improved predictions, and they all showed similar performance. Expressions over Canadian tends to be a little bit conservative, and the expressions given by Aziz Namini produce excessively conservative predictions and is not recommended for the use. So let's move to the other design code provisions on the possible effect of the change of stress block. Chapter 18, prestressed concrete has one design expression which has a beta 1 parameter. We studied two cases. Case 1, tendon only. And basically what we have done is we calculated code predicted tendon stress using different beta 1 expression. And if you look at the results, the variation is less than 2 or 3% at most, so which is negligible. Similar observation can be made for case 2, where compressive and tensile reinforcement is included in the section. When you look at the Appendix A, they do have two design equations. They are the equations for calculating effective compressive concrete strength in a strut and in the nodal zone. The Bahen and Sanders already studied the impact of the increase of concrete strength on the calculated concrete strut. And as you can see, as concrete strength increases, the code starts over-predicting the concrete strut strength. And first figure shows when there's no reinforcement. Second figure shows there is some reinforcement with or without satisfying the code requirement. So I can say that the beta 1 the impact of the change of concrete stress block has negligible impact on chapter 18. However, Appendix A has some issues with the concrete strength because of the current expression of alpha 1. More research will be required to come up with a stress block expressions which can be used not only for beam and column design, but also the strut and tie design provisions. And I already made some the same conclusions and stated repeatedly. So this is all my presentations.